Before ChatGPT, before Transformers, and before Word2Vec, how did we get computers to understand text? Computers don't understand text, they understand numbers, vectors. To bridge that gap, you would have to convert sentences like this into vectors. And historically, it all started with a concept called bag of words. Hi, welcome to Bag of Words. In this channel, we will deep dive into both math and code behind NLP as well as AI/ML concepts. In this video, I will explain what Bag of Words is, we will see TF-IDF, and then we will code these concepts in Python from scratch. So let's get into it. Imagine you take a sentence, tear it up word by word, and throw them all into a bag. Now you shake it up. What happens? You lose the grammar and the order of the original sentence, but you still have the count of each word. That's the whole idea behind Bag of Words. Now let's look at an example. In NLP, the entire dataset is called corpus. In this corpus, we have two documents, doc1 and doc2. Step 1 is to identify all the unique words in our corpus and then sort them alphabetically. The resultant will be our vocabulary. Now step 2, we convert these documents into vectors by simply counting how many times each vocabulary word has appeared. Doc1, we see cat has appeared one time, there's no cheese, there's louse one time, mouse appears one time, the appears two times. Similarly, doc2, cat doesn't appear, cheese appears one time, loves appears one time, mouse appears one time, and the appears one time. Now just like that, we have converted the text into a vector. Now there are two problems with this. First is we have lost the order of the sentence. The model doesn't know the difference between cat loves mouse or mouse loves cat. Second, look at the word the. It has the highest score in the document 1 simply because it appears a lot. But does the word the has any meaning? No, it's just noise. To fix this frequency problem, we have to upgrade our bag of words using a technique called TF-IDF. But before we look at the math behind TF-IDF, let's jump into our IDE and code bag of words from scratch. Alright, we are in Google Colab and I have already written our corpus in a Python list. Now as we learn, we have to first identify all the unique words from our corpus. We'll first create a variable called vocab and assign it an empty set which will drop any duplicates. Next, we'll write a loop to go through each document in our corpus. Then we will again iterate through each word in our document. We will lower and split it in order to get each word. Then we will simply add it to vocabulary. Now, the next step would be to sort them alphabetically. So we can use sorted function of Python to sort them. Next, we will print and see our vocabulary. Now we need to create the actual term count, which is our bag of word matrix. Let's create an empty list called bag of words, which will hold the final vectors. We will loop through each document in our corpus once again and split the document into lowercase list of words. Now we will initialize a temporary vector filled with zeros, matching the exact length of our vocabulary. Then we will loop through each word in our sorted vocabulary and we will replace those zero with the actual count. Finally, we will append our completed vectors into our bag of word list. To make this easy to read, I have imported pandas and put our list into a data frame. Now let's print and see our final result. To fix the bag of words problem, we use an algorithm called TF-IDF. It stands for term frequency and inverse document frequency. First is term frequency. Instead of just using raw count, production systems often use a technique called logarithmic squashing. The formula looks like this: log base 10 of the word count plus 1. Why do we do this? Imagine the word the appears 1000 times in a document. The math will make it log of 1001, which is just 3. Now imagine the word data which appears only 10 times. The math will look like log of 11, which is 1.04. By using logarithms, the massive misleading gap between 1000 and 10 has been heavily reduced. It stops the model from assigning deep meaning to high frequency words just because they appear a lot. Now let's look at IDF. It basically asks how rare is a word across all documents. The formula for IDF is log of total number of documents by document frequency, which is how many documents actually contain that word. From our previous example, the word the appears 2 times and cat appears 1 time. Let's implement those in IDF. So for the, we get log 10. We have 2 documents and it appears 2 times, which is basically log 1, which is basically 0. And the word cat, it appears only 1 time in both documents, which will give us around 0.3. Finally, we take our term frequency and multiply it by inverse document frequency to get TF-IDF. Mathematically, TF-IDF neutralizes the words which appear everywhere. Now that we understand the math, let's jump back to Colab and code this exact same logic. Alright, we are back in Colab. To save time, I have pasted the complete TF-IDF logic here. But let's walk through it block by block so you can see exactly how our whiteboard math translates into Python. First, we calculate the term frequency. We loop through our bag of words counts, and for every word count, we apply our logarithmic squashing. Right here, we take math.log10 of the count plus 1. Next is the IDF. We set n to the total number of documents. Then we loop through our vocabulary, calculate the document frequency, which is simply counting how many documents contain that specific word. And we apply our formula math.log10 of n divided by document frequency. Finally, we bring it all together. We create our final TF-IDF list, loop through everything, and for every single word we multiply its TF score by its IDF score. Let's put this into a pandas data frame and run the cell to see the final output. As you can see, the word the, which used to have a score of 2, has been completely neutralized to exactly 0 because it appears everywhere. But the word cat survives with a positive mathematical score. Now that you understand the math behind TF-IDF, I have a confession. In the real world, you are never going to write this from scratch. In the real world, you will use a library like scikit-learn, which can do everything we just did in 3 lines of code. We will import TF-IDF vectorizer, initialize it, and run fit transform on our corpus. Look at the word the. In our manual math, it was exactly 0, but scikit-learn gave it a score of 0.7. Did we do the math wrong? No, we did the textbook math perfectly. But under the hood, scikit-learn automatically alters the formula. First, they add a constant plus 1 to the IDF equation so that common words aren't completely erased. This is called smoothing. Second, they mathematically shrink every vector to a length of 1 called L2 normalization. This is the difference between learning textbook theory and actually writing production code. So bag of words gets us text and IDF tells us which words actually matter. But we still have one massive problem. Neither of these models actually understand meaning. To TF-IDF, the words king and queen have no relationship to each other. They are just isolated numbers. If you want our computers to actually understand the context and meaning of human language, we have to upgrade to word embeddings and Word2Vec. And that is exactly what we are building from scratch in the next video. If you want to master NLP and AI, make sure to hit the subscribe button. Also, I have created an immersive blog post on everything we have just talked about. So if you ever want to recap the math or revise this concept later, you will find the link to that blog post down in the description along with the Google Colab code. Thanks for watching. See you in the next one.